In this lecture, we're going to talk about the terrestrial planets and just their orbits in geology. In the next lecture, we'll talk about a couple more features of the terrestrial planets, like atmospheres and things called magnetospheres, which in fact all planets have, but this is the first time we'll see them. So this is a cartoonish version of our solar system. And what we're going to do is break it into collections of objects and then slowly talk about each group and work our way out from the sun to the far edges of the Oort cloud. So closest to the sun, there's a collection of so-called terrestrial planets, and then after that, we'll talk about the asteroid belts. The vast majority of asteroids are in between Mars and Jupiter. After that, there's the collection of so-called Jovian planets, like Jupiter and Saturn, and they're very gassy and large. And then after that, the Kuiper belt. This is now where Pluto resides. It's the king of the Kuiper belt instead of the runt of the planets. And then finally, the Oort cloud. And we'll talk about these two groups together because this is primarily where comets come from. So, in fact, this is true for all bodies in the solar system. And as far as we know, all astronomical objects everywhere. Their orbits are completely determined or could be completely described by Newton's laws of motion. So force equals mass times acceleration, and the force in question is gravity, the attractive force of gravity in between things. For the biggest 5 planets and a large number of other planets, you also get Kepler's laws. So Kepler's laws fall out of Newton's laws of motion in the case where only the sun's gravity is important. And that's true for the 5 closest and largest planets, so Mercury, Venus, Earth, Mars, and Saturn and Jupiter. So the 5 closest planets only really care about the sun's gravity. And then after that, you might have to worry about another close interacting body. But certainly for these things, Kepler's laws work really, really well. Kepler's laws also work really well for farther objects that just don't interact with anything else. So for instance, this is a really elliptical ellipse that describes the orbit of Halley's Comet. For other bodies, especially as you get farther away from the sun, you might get things that don't quite obey Kepler's laws. And the criterion for not being able to be described by an ellipse with the sun at the focus and be a perfect Keplerian orbit is basically there's a second force. So as long as there's any other force that you can ignore that's not gravity from the sun, you won't get a nice Keplerian orbit. So for the pair Uranus and Neptune, in fact, again, this is how Neptune was discovered, is that the orbit of Uranus isn't a perfect ellipse, it's wobbling a little bit, and that led people to look for the thing that was causing it to wobble. And if you look at the asteroid belt, we talked a little bit about these gaps in it, and what these gaps represent is these systematic pulls from Jupiter. So this asteroid, for instance, goes around 3 orbits, Jupiter goes around 1 orbit. They keep lining up in the same way, and then Jupiter will tug them out slowly over the course of hundreds of millions or billions of years. Secondly, there's this group here and group here that we'll talk about when we talk about asteroids. They're also being held in by the gravity of both Jupiter and the Sun, so they don't obey perfect Keplerian ellipses. And then finally, in the age of space exploration, we can generate very non-Keplerian orbits. So this line is, the red line is a trajectory of an asteroid rendezvous spacecraft that was made by American engineers and scientists and launched in 1997. And this certainly isn't a perfect ellipse. And the thing that's making it non-elliptical is the rocket engine itself, so providing a little extra force to have it fly by and change its trajectory and end up rendezvousing with us. Okay, so you'll see more and more examples, but essentially, thanks to Kepler and Newton, we understand the motion of the objects. So now as we go through this tour of the solar system, the 2 remaining questions that we have are, what are the objects' structure? So we'll go through and consider what it would be like to cut one of these objects in half, a Jovian or a terrestrial planet, and see what's inside of it. And then secondly, answer the question of what it's been doing over the last 4.5 billion years. So has the Earth always looked the same way? Have the Jovian planets evolved, or they always looked like they do now? And then what's going to happen to them in the future? So their evolution. And these are our 2 remaining questions. So first off, a definition. So we're going to talk about the terrestrial planets. Sometimes you hear them talked about as Earth-like planets or inner planets. I think of those names, inner planets is the worst now that we know stuff about other solar systems that are not our own. I like terrestrial planets. It's basically a fancy way of saying they're like our planet. So they're rocky. They probably have some sort of atmosphere, even if it's a really thin, primitive one. A lot less than the outer planets, but even the moon, in fact, has a really tiny, sad atmosphere. They have very few moons. In fact, Earth is an anomaly because we have this very large, it's almost a coplanet in some sense. And then in our particular solar system, they're close to the sun, in between about 1/2 and 5 astronomical units. So what we're going to do is we're actually going to talk about the moon as if it were a terrestrial planet, because in composition, it actually belongs in this group. For instance, if you were to cut Mercury in half, Mercury would be more similar in structure to the moon than it would be to Venus or Earth. So essentially, based on how it looks and what it's made out of and how it's evolved in structure, it is a terrestrial planet, quote unquote. It's a moon in terms of its orbit. So it's a natural satellite of Earth. It's not orbiting the sun primarily, it's orbiting the Earth. So it is a moon. We're throwing it in because now we're talking about structure and evolution. And you're highly encouraged to click on this link if you want to hear a very erudite discussion of whether or not the moon is a planet or a moon. Okay. So here we go. We're going to cut them in half, and it turns out that more or less all of the terrestrial planets have a similar feature, where in the center of them there's a collection of really heavy metals. In the case of Earth, it's iron and nickel, and this is the core. Outside of the core is a mantle of primarily molten or half-molten rock, kind of plasticky, if you imagine. You've seen lava flowing out of a Hawaiian volcano, and it's very thick and viscous, so that kind of half-molten rock. And then a crust and an atmosphere and some other stuff that we'll discuss. For this class, the parts of the atmosphere are not important to learn. We just say an atmosphere. And if you think about the structure, you realize, kind of unsurprisingly probably, is that the denser material is at the center of the terrestrial planet. So iron and nickel are very dense. If I have a handful of iron and nickel, it weighs more than a handful of molten rock, which you probably don't want to have a handful of anyway. And then even lighter still is a handful of the types of rocks that you would find on the crust of Earth. These are actually kind of fluffy rocks. And then lighter still is atmosphere. So the idea of, or the process of pushing denser materials to the center and fluffier materials make their way to the outside, this is what's called differentiation. And it's absolutely no different than when you see salad dressing separate into the oil and the water parts. So all it means is that if you let something have enough time, what's going to happen is the dense material will sink towards the center, and the less dense material will pop out towards the top. And amazing aspect of YouTube is that you can literally type anything into it and get a video response. So if you type in time-lapse of salad dressing, you will see a time-lapse of salad dressing. And this is differentiation. What you can see is the heavier material sinks towards the center and the lighter material will come out towards the top. So let's look again at the beginning. You can actually see individual bits being pulled one way or floating up to the top. Less dense, more dense. If you give something the size of Earth 4 billion years, it will do the exact same thing. Okay. So all of the terrestrial planets have done this. And if you were to cut them in half, a good question is, how do you know what's inside of Mercury? And we'll talk about that on one of the exercises. So all of them will have the feature of crust, mantle, core. And the core will be heavy metals, the mantle will be heavier, more molten, compressed rocks, and the crust will be lighter stuff. Now the exact proportions of them are different, and it's a little bit unclear how legitimately core-like and metally the moon's core is, but they've all been differentiated. Well, so that was easy. So now we want to talk about evolution. And if you stop for a second and brainstorm, and somebody asks you the question, what on Earth, well, what in the solar system could happen to an Earth-like planet over the course of its, 2 billion or 4 billion year life? List everything that could change the shape or the face or the appearance of a planet. You list them, you say well, it could be exposed to space weather like solar wind. Here's a picture of a large impact. In fact, this is an artistic representation of the formation of the moon. So obviously things get hit by impactors, but then on Earth we have other processes that reshape the face of the Earth. We have earthquakes, we have volcanoes. So you list all these things, and what you would get is that they essentially fall into two groups. They're what you would call internal influences and external influences. So internal influences on a planet are the things that they kind of do to themselves. Volcanism, plate tectonics like earthquakes, and then just normal weather erosion. For instance, if you have a soil cliff after thousands of years, it won't be there anymore because rain and atmosphere has removed it. The second class is external, which is the stuff that the rest of the space environment does to the terrestrial planet. And external influences include collisions like from asteroids and comets, tidal influences, pretty subtle, but we've definitely influenced the moon. It used to be spinning, and we basically have ground it to a halt, so the same face always faces us. That is definitely an influence that we put on the moon. And likewise, the sun and the other planets are really slowly tidally influencing us. Not as much, but it's still there. And then finally, space weather. This would be like the solar wind coming by. And it turns out the solar wind is in space weather is a really large influence in certain terrestrial planets' evolution. So this is the internal and the external influences, and there are more, but this is these six basically explain most of the change in the face and structure and appearance of the terrestrial planets. So that in mind, it turns out that the terrestrial planets come in two varieties. So here's some representative pictures from the surfaces of them that will start cluing you into this drastic difference in behavior. So this is a picture from the surface of Mercury, and what you see is craters inside of craters inside of craters. And it's not that Mercury is particularly unlucky. It still, maybe gets hit by a large impactor every, 50 million years or something like that. But what Mercury isn't doing is Mercury isn't like repaving its surface. And I don't see any internal influences. I don't see any weathering or erosion. There's no plate tectonics shuffling them around. There's no volcanic activity covering them up. So this really shows me that Mercury is completely devoid of internal influences. Likewise, in a very extreme case, this is Neil Armstrong's footprint on the moon. It's still there over 40 years later. 40 years from now, it'll still be there. There's nothing that's going to remove this footprint, barring, impact. So none of the internal influences like erosion or weathering or plate tectonics. Whereas conversely on Earth, not only will a footprint not last for 40 years, even during the course of our lifetimes, 40, 80 years, this mountain, Mount St. Helens, has been basically cut in half and it's starting to rebuild again. So not just footprints, but mountains themselves can disappear and reappear over the course of a lifetime. And similarly, this is a picture from Venus. This is Venus's version of Mount Rainier. It's actually a dual volcano. You can see both of the little pits. So Venus also has an incredible amount of atmospheric activity, and it's got evidence of volcanic activity as well. And then somewhere in the middle is Mars. So here on Mars, you can see evidence of multiple craters. So the craters don't seem to be repaving. But then I also see evidence of what seem to be erosion, these channels coming by. So the two varieties that terrestrial planets seem to come in are no internal influences whatsoever or internal influences. So again, some planets have erosion, plate tectonics, and volcanic activity, and some of the terrestrial planets do not. The way that we describe this is through the phrase, and I emphasize the quotes, geologically dead and geologically alive. So this has nothing to do with biological life. This really just has to do with the fact that the surface of the planet itself is or is not constantly refreshing itself. And, for instance, it's almost as if you cut Earth, it would bleed. The blood would be lava, but the analogy is that it's still alive in that sense. Whereas, you put a footprint on the moon and it'll be there for a century. So Moon and Mercury are absolutely geologically dead. You put a little scar on them and it'll remain there for a really long time. Whereas Venus and Earth are very geologically alive, so their surfaces are constantly changing and repaving. If you punch through the crust, what you'll get is, magma coming out. And then in the middle, Mars is either almost dead or recently deceased, depending on how you want to think about it. There's evidence of volcanic activity in Mars's past. This is on the top. The picture is of Olympus Mons. It is the largest volcano in the solar system. It's about 3 times the height of Mount Everest. And it's actually also wheelchair accessible because the slope is so gentle. And then down here we see evidence of old erosion, but then craters that have shown up more recently and have not been eroded or repaved. So the question is, why do the terrestrial planets split themselves into these two groups, the geologically alive and geologically dead versions? And there's a clue as to fundamentally why it is, but the kind of technical answer has to do with what's called the lithosphere. And the lithosphere is all of the crust of the terrestrial planet and the part of the mantle that is dried up and solid. So you can think about it as the thickness of the hard crust on the planet, and that's, essentially what it is. It turns out that Earth and Venus have very, very, very thin lithospheres, so very thin hard crusts. In fact, if you wanted to dig down through Earth's surface until you got to the liquid part, it would only take you about 30 kilometers, which, if you imagine driving 30 kilometers, it's really not that far in between you and an ocean of liquid rock. So think about that when you're trying to get to sleep. Likewise, Venus also has a pretty thin lithosphere, and these diagrams are not quite to scale. It's, again, a cartoon. But if you look at Mars, Mercury, and the Moon, their lithospheres are really thick comparatively. Not just in proportion to the planet's body, they are actually really thick. So what is it that a thick lithosphere does? Well, if you have a huge shell of hard, dry rock, what that means is that you can't get volcanism and you can't get seismic activity. So a volcano basically is the liquid part of Earth bubbling out to come in contact with the solid part, the crust. So an intrusion from the mantle to the crust. And if it has to fight its way out through, 500 kilometers worth of rock, it's probably not going to be an active volcano that makes it all the way to the surface. So thick lithosphere means that you really can't get a volcano. And then a thick lithosphere, we'll talk about it in a second, means you also can't get plate tectonics, which also repaves the surface of the planets. So why is this? So fundamentally, and you can look at the planets and you get a sense that there seems to be some trend there. It's the bigger the planet, the smaller the lithosphere, which might seem a little bit counterintuitive. But one way to describe it is imagine that you cooked 3 potatoes, so you put them in boiling water and left them there until they were cooked through. They're all the same, really high temperature. One of the potatoes is really big, one of the potatoes is medium-sized, and the other potato is really small. Which one do you want to eat first if you're hungry after you take them out of the water? It's the small potato, because the small potato will cool the fastest. So all of the terrestrial planets and Earth's moon were formed basically at the same time, but the smaller ones have cooled off faster because that's just what small things do. So the moon has cooled off and its lithosphere has become solid, and Mercury has cooled off and its lithosphere has become solid. Mars is the next smallest, is almost completely solid. Its lithosphere is really thick. And the big planets, Earth and Venus, will take longer to cool down, so they still have thin lithospheres, and their interiors are still a higher temperature. So it's really that. Okay, so what this means for the tectonic activity, obviously thin lithosphere means that lava and magma can't get out, so there's your volcanism. The seismic activity comes from the fact that the tectonic plates are basically riding on a thin crust of, or thin plates riding on a crust of molten magma. And this is something that in the context of gases, but it's true about everything. So hot things rise and cold things sink. And slowly, over the course of millions of years, what's happening inside the Earth's mantle is that hot rocks are actually rising and cooler rocks are sinking, cooler magma. And this is a very, very slow process, but it's still happening. And so as these conveyor belts of hot magma rising and cold magma falling circulate, the solid part, the lithosphere riding on top of it, either is pressed into plate against plate, and they'll crunch together and form mountain ranges, or they'll pull apart and fall what are called graben. They're more or less stretch marks on the surface of the planet. As the tectonic plates are ripped apart, you see these trenches, and these are actually graben and valleys on Mars. So this is where two tectonic plates would be pulling apart. And just to give a sense of how universal this is, it's literally the same process that you would see in a lava lamp. So somebody just turned on this lava lamp, and the heat source is down at the bottom. What you'll see before it really starts getting going is the hot stuff will, or the wax near the heat source will heat up, rise to the top, cool off, and sink back down. And before it really gets kind of psychedelic, it'll establish a circulation pattern, much like we do in our mantle. So yeah, I think we can do without the music. So wax starts to melt, and then now you see the hot wax rising along this side and then falling. And it's made it into a little circulation pattern. And this is about as close as you can get to demonstrating what the mantle is doing, because it's kind of semi-solid. The frame rate might be kind of low, so I'll post that link. Okay. So a question that comes up is, okay, if I want to reanimate a planet and turn it geologically alive from geologically dead, what's causing that? For instance, why doesn't the sun melt Mercury again? It turns out that sunlight is not a significant source of heat on the scale of an entire planet. So planets are, the Earth is 10 to the 24th kilograms of rock and metal. And sunlight just does not provide enough power to be significant. So the sources of heat that we're talking about, what made the planets hot in the first place, is the contraction from the original cloud of gas that our solar system formed from, the friction from differentiation. So as the metal sinks towards the center and the hot stuff bubbles out towards the top, it grinds against each other, and that provides a source of heat. There's also a little bit of radioactive material that got trapped inside of the planets. It's also true about the asteroid belt, and there's some really interesting radioactively cooked asteroids. But, for instance, the uranium ore that is contained in the Earth's crust, it's a non-negligible source of heat. And then accretion, which is a very delicate way of saying stuff hitting us. So let's say that you want to colonize Mars and you want to turn it from geologically dead to geologically alive. And there are reasons to do that. You're probably not going to be able to transport enough radioactive material and bury it. It's already done differentiating. It's already done contracting. So what you'd really have to do is maybe steer an asteroid in an unstable orbit and smack into Mars. And in that way, you could provide enough energy to melt the lithosphere and get it geologically alive again. And maybe you would get, Olympus Mons going off again and tectonic activity. And we'll talk about the other effects of that magnetosphere and atmosphere in the next lecture. But this is really it. So if you want to unzombify Mars and reanimate it, you could steer a big asteroid into it, maybe. Okay. So the two geologically dead planets, there's actually evidence that they were in the far past geologically alive. So this is one of those what are called Mercator projections of the entire surface of the moon. This is the type of map that would show Antarctica as covering the entire bottom half. So everything's spread out. And what these dark flat parts are, these lava plains on the moon, were from when the moon was geologically alive and it was liquid, and this is basically dried lava. This is dried lava, but it came from an impactor that punched through the core, and dried lava. So the old lava plains on the moon are evidence that it was at one point in the far past, billions of years ago, geologically alive. Likewise on Mars, this is one of those so-called graben where two tectonic plates were pulling apart, this long trench that you can see. And then within that trench, you can also see evidence of weathering. So this is a landslide, basically, and it's a huge landslide. This is 200 kilometers, so it's about half the size of the state of Washington. So this is a really big landslide, large geological event, and you probably couldn't have this without some sort of atmosphere, flowing water, or potentially seismic activity. So more evidence that Mars was geologically alive in the past. And in fact, you could argue that Mars is barely clinging on to geological life in a sense. So these are high-resolution images from a satellite that was sent to Mars and orbited it and took pictures for years. And these are evidence of gullies and avalanches. And you could ask how old they are. And it turns out people were really excited about this, is that over the course of the multi-year mission of the satellite, this is the exact same spot. So this is the same exact location on Mars. And if you look here and here, there is still weathering going on Mars. So there was a little bit of a gully and a little avalanche, and you could almost convince yourself that this is a mudslide or that there was some sort of liquid there. Liquid water really can't exist on the surface of Mars. We'll talk about that next time. But Mars is still weathering. And that's now the kind of missing piece where, hopefully you're convinced that the thickness of the lithosphere will determine whether or not you have tectonic activity and volcanic activity. But now we also said that weathering and erosion and atmospheres are also internal processes that can happen to a terrestrial planet. What on earth does that have to do with a lithosphere, if anything? And that will be the next lecture. So as always, here are the great slide with key terms and the questions that if you can discuss over the course of 5 or 10 minutes with your colleagues, then you have a pretty good understanding of this material.